Welcome to the next video lecture. So in this video lecture, we will discuss about as we said, like it as in the next video, in this video, we are going to design an electrical system of a mathematical modeling based on transfer function. Okay. So topics to be covered is totally mathematical modeling of an electrical system using transfer functions, not using any other things. Okay. So in this total lecture, it will be a little bit of big one. So please see this very carefully. So next one is the this is part two of that mathematical system. You already know like it as a. So we will discuss about a here in this thing we are going to discuss about two examples. One is about one basic RLC circuit and another one is the low pass RC filter. Okay, so these are the basic two circuits where if you can understand, you can able to design a complex circuits. So in this totally what we are having is a RLC circuit which is having a R, L and C both are in three are in series is connected to a input voltage of AC voltage system. Okay, the same circuit I am taking this one. So in the time domain, how we need to represent this thing means, so first we will go with the step by step thing. So whatever the resistor will be there, the resistors we are not having any variation with respect to the time. So that's why V equal to IR. So there is no change will be there. But when it comes to the inductor, it is varies with respect to the time. So that's why it is representing with respect to the voltage like the V equal to L di by dt. In the same way, the capacitor I equal to C dV by dt. So these are all the basic formulas. So here, if you see here, so we are having a things called it as a totally three things are in series. So using what how we did this using Kirchhoff laws and also the Laplace transforms, we need to first derive the electrical circuits as a transfer functions. Okay, so these two things we are need to understand. So then again the same circuit we are considering. So example like it as a we are considering like it as a V in as an input voltage and V out as a output voltage where it is staying it in, across the capacitor. Okay, so then so using KVL. So initially using KVL, how we need to define is a V input equal to Ri into Ri of t and L dI by dt and 1 by C integral of I of t dt, because current is the changing thing. So that's why we are representing all in a Kirchhoff law form, so KVL form. So that's why we are doing this one. Now what we need to do is we need to convert this into Laplace transform. So we are applying in Laplace transform. Okay, in Laplace domain, how it will be changes means V in of I of V in of S. That means S domain. Laplace also Laplace domain means S domain. We need to take it. So R plus SL plus 1 by SC. In whatever the I of t is common is there, so I of t is completely taken into consideration of I of S of S. It is having a multiple, a couple of steps will be there, but I am considering this as a completely as a one output. So because to make it in a crisp video. Okay, and if the output is across a capacitor, if the completely like it as a, if the output is across a capacitor, then what will be there means V out of S will be equals to the 1 by SC I of S. So if I want a transfer function means of a complete model means I need to consider like it as a, we need to take the total transfer function in a time domain means we need to take with respect to the output and also input. So to consider the transfer function, that one V out of S by V in of S. So I will get the simple equation I of S and I of S will be get cancelled out. So 1 by SC by R plus SL plus 1 by SC will be there. So this is the final equation. But if I even till also solve the another little bit of more steps means, then what will happen is, so it will be considered like it is 1 by LCS square plus ECS plus 1. ECS means I can simply like take it as a E means with respect to the these things like with respect to the voltage. Okay, so this is how it will be happens. Okay, plus 1. And the next one is about we will consider with respect to the another example that is called the low pass RC filter. Because why we are considering low pass RC filter, because RC filter or LC filter mostly always many places it will be used in the power electronic domain. Okay, and also control system based things. So that's why we are using that one. So we are seeing the circuit diagram of a RC filter where it is having an input of V in and R and C both are connected in series, and after that output is considered as in V out, which is having it in parallel. So as before itself I already said like it as a, if the output is across the capacitor means what will happen, V out equal to 1 by CS V 1 by C of S will be there. So the same thing it will be represented here also. So RC filter, so whatever the RC filter circuit will be there for an RC low pass filter, what I'm considering is I'm getting a final equation here. The final equation is this one. V out of S by V in of S is equal to 1 by RCS plus 1 will be there. So before whatever the now I'm getting the total final equation as a transfer function, but it is having a little bit of initial before steps will be there, like with respect to the input and also with respect to the output. Both we need to write equations, and after that only we need to take a transfer function in a final step. So this shows what it will happen is it can show it like it as a how it a system or how a RC filter will operate, R and C will operate with respect to the frequency. If the frequency changes, resistance will not, maximum will not be changes, but the system will change, capacitor will change with respect to the frequency. So then with respect to the frequency, size may decrease, and also with respect to the frequency, the capacitor operation will be different. So these are the things it will happen. So here these are the models based upon a control system where we can able to identify like it as a this RC filter wherever we are applying this. We can also see it as in power electronic circuits like as a RC filter we will say it as, or a filter circuits, and audio filters. In audio filters means simply like it as a, recently we are seeing like it as a noise cancellation or noise filtering. The headphones will be there. What are they doing is they are cancelling out the that noise with respect to this capacitor and resistor. So unwanted noise, unwanted things will be eliminated by this one. So this is how it will be operates. And the calls communication circuits, so to make a smooth communication or smooth transfer of the voices and everything, it will be useful. So we have the transfer right now we have a transfer function. So then we can easily control like it as a how we can able to control with respect to the S domain analysis. Okay. So but by this video on before going to the control aspect, so I need to say it like that there are certain aspects you need to remember on all the control system time wherever we are doing it as there are multiple things are there always. Okay, so assumptions will be there. So in the initial assumptions like it as a assume the zero initial conditions unless stated. That means unless stated means if they are not giving or if they are not saying anything means then you need to consider like as a zero initial condition. If they are stating means then you need to consider. For example, sometimes you need to the people will in the question, sometimes in the problems we will see like it as a in the negative instant or in the -1 instant, -2 instant that they will give. That means then initial conditions will be considered like as a -2 or -1. But here whenever the -2 no conditions are given, then initial condition will be considered as zero itself. And the next one is about use Laplace transform for easy manipulation. Manipulation means to make things in a very less certain, because whenever you are going into a differential equations or some in different format of mathematical equation, it will may about sometimes it may go to the beyond extent. So that means a more mathematical part will be increases, but when it comes to the Laplace it will be make very less things. And also what are the units are there that need to be dimensional consistency. That means sometimes whatever equations are there, that equations all need to be in a time domain or all need to be in one format itself, or need to be in voltage equivalence, or all need to be in current equivalence. In this way only it need to be there. So these things you need to take care of when you are writing one equation. And also use system analogies. That means whenever you are converting one mechanical system to electrical system, as we discussed in the previous videos, so like it as a force to the velocity or inertia to the something else, and capacitance, inductance, and also resistance, damper to resistance. These are all the things will be there. So these are all need to be considered. Then only we can able to give a perfect physical system into the mathematical modeling. Then only we can do. Okay. So in the next model, next video lecture, we are going to discuss about the how a DC servo motor we are going to change convert into mathematical modeling. Till now we discussed about a one physical model, and when that means a mass damper spring system, and also one RLC circuit, one RC filter circuit we discussed. But now we are going into a little bit of deeper, that is called it as a DC servo motor, where we are using and what is that one and how we are going to convert into a mathematical modeling. Okay, thank you.